Hi everyone. Today let's talk about session 2.2, more methods of proofs. First, proofs by contradiction. So a proof by contradiction establishes P implies Q by we assume the hypothesis P is true and the conclusion Q is false. And then so we're using P and not Q as well as other axioms, definitions, previously derived theorems, and the rules of inference to derive a contradiction. So once we get a contradiction, that it means what we assume the Q is false is wrong, so it must be true. Okay? So a contradiction is a proposition of the form R and not R. R may be any propositions, whatever. So which is impossible. Because we cannot have R and not R in the same time. So they're opposites, okay? A proof by contradiction is sometimes called an indirect proof. Let's look at the following examples. Give a proof by contradiction of the following statements. For every n in Z is integers, if n squared is even, then n is even. Okay, so notice that the direct proof is hard because, let me put it down here. So notice that the direct proof is hard because you want to start with n squared is even. Well, n squared is even means n squared equals 2k for some k, and you want to find out n is even, so n is 2l for some l. This is hard because how do you get from like n squared to n? Can you take square roots? No, we can take like a square root of 2k. So in this case, the direct proof is hard. So let's try to use proof by contradiction. Okay, so proof by contradiction. So proof by contradiction, we assume, okay, so we assume the P and not Q. So we assume that for every n integer, okay, so we let n be an arbitrary integer. We assume n squared is even and we assume not Q, so n is not even, so which means n is odd. Okay, so because n is odd, so since n is odd, then we have n equals 2k plus 1 for some integer k. You can also say since n is odd, there exists some integer k such that m equals 2k plus 1. But I just find this way is shorter. But there are a lot of lot of different sentences you can prove the same thing, right? It's just the different sentences they represent the same thing. Okay. Now, we have the n is odd. Then let's see what is n squared. Well, n squared is then 2k plus 1 squared. Okay, how do we square it? Okay, let me recall you what formula we use. So a plus b squared is a squared plus 2ab plus b squared. A minus b squared is a squared minus 2ab plus b squared. Okay, so in our case, we have 2k squared plus 2 times 2k times 1 plus 1 squared. 2k squared is actually 2 squared k squared, so it's 4k squared. And then 2 times 2k is 4k plus 1. Oh, what happened? Is this guy odd or even? This guy is actually odd, right? If it's odd, we want to put it in the format of 2 times an integer plus 1. See, the 1 is already there, but for the previous 2 terms, when we factor out 2, what's left? We have 2k squared plus 2k. So far, so good. Now, this is an integer. See, we have shown that n squared is 2 times the integer plus 1. So, by definition of integer, n squared is odd. What happened? Do you see something? Oh, we get a contradiction. 2 n squared is even. So see, we derive a contradiction, which means whatever we assume is wrong. N is not odd. So therefore, or hence, n is odd. So far, so sorry. N is even. Okay. Yeah. Okay. So our assumption n is odd is false. So n is not odd, then n is even. Okay. Yes. So sometimes you finish the proof. It's very important to check your proof again. Maybe sometimes you can find a mistake. Okay. Yeah, we could go check again. First, we let n be arbitrary integers. Then we assume p and not q. So p n squared is even, not q. So n is not even. So n is odd. And then we it's better to look at the n, because the n squared, you cannot take the square root of n squared. So that's why we look at the n. Because it's odd, then n is 2k plus 1 for some integer k. And then we want to compare with n squared, so we can square it. Square it, we know how to calculate the square, right? And then we realize, oh, the format is really like an odd integer, right? So that's why we express it as 2 times something plus 1, and this is odd. So then we get a contradiction, so which means n is not odd, so n is even. That finished the proof. So far, so good, everybody. Okay, next example. Remember, when you play the videos, you can stop at each example and then try the problem first, and then you continue to play the videos and check your answers. Okay. So given the proof by contradiction of for all real numbers x and y, is if x plus y is greater or equal to 2, then either x is greater or equal to 2 or y is greater or equal to 2. Okay, so let's see here. So, okay, we want to prove by contradiction. Okay, so let x, y be real numbers. And we assume, we can say assume or suppose p and not q, right? So p is x plus y is greater or equal to 2. Not q. Okay, not q. You see, here we have, let's say this is R or S. Okay, this is the, let R be the proposition x greater or equal to 1, S be the proposition y greater or equal to 1, then what is not R or S? This is not R and not S, which means x is not greater or equal to 1, so x is less than 1, and y is less than 1. Okay, this is what we assume. Okay, now let's see. Well, we have x less than 1 and y less than 1. Let's say this is equation 1, equation 2. When you add those equations, what happened? You have x plus y less than 1 plus 1, which is 2. We can do that only if the inequality match. Okay, we have to make sure the inequality match. Then we can do it this way. Okay, and well, we have x plus y is less than 2. Ooh, we get a contradiction to the fact that x plus y is greater than or equal to 2, because we get a contradiction, which means the not q is false, so q must be true. So therefore, we say hence either x greater or equal to 1 or y is greater or equal to 1. All right, so far so good, everybody. Okay, let's continue. Do you have the same answer? Okay, next example. Okay, so this example is, I would say, the most challenging examples. Okay, so let's do it together. Prove that square root of 2 is irrational using proof by contradiction. Okay, now let's see. Proof by contradiction. Write it down. So when you use proof by contradiction, please write it down, okay? Then I know that you're using proof by contradiction. Okay, not a direct proof. All right. So what do we assume? We assume proof. Okay, so we assume square root of 2 is rational. Okay, so here we don't have P, we just have Q. So Q is the conclusion. So we assume not Q. So we assume the square root of 2 is rational. Well, then rational means square root of 2 is P over Q for some integer P and Q. Okay, let's also assume that P and Q, okay, so P and Q is in the lowest terms. Okay, so we should say, let's assume P over Q is in the lowest terms. That means P and Q, they don't have common factors. We can do that because if you see a common factor, you just cancel that common factors. So we have the lowest terms. Okay, so far so good, everybody. Okay, so because they don't have common factors, so we have P and Q are not both even. So, i.e., one of them is odd. Think about it. If both of them are even, then you can say, oh, this is 2 times K, this is 2 times L. Then you can cancel the 2. So see, they're not in the lowest terms. So so P and Q are not both even. One of them must be odd. Okay. So now let's continue. We have square root of 2 equals P over Q. Let's square both sides. What do we get? Okay, then we get 2 equals P squared over Q squared. Right? This is the same as when we multiply both sides by Q squared, we get P squared is 2 times Q squared. Ooh, Q squared is an integer, so we know P squared is even, right? And because by the example we proved before, okay, so by the example we proved before, like n is even implies n is even. So n squared is even implies n is even. We know the P is even. So far so good, everybody? Okay, so because it's even, then we say P equals 2K for some integer K. All right. Then now let's plug in. We get p squared. So p squared is 2k squared equals 2q squared. Well, 2k squared is like 4k squared equals 2q squared. We can divide it both sides by 2, and let's move the q's out. Let's switch them. So q squared is on the left hand side. Then q squared equals 2k squared. Oh, what do we see? So q squared is even. Well, then by, let's say this is the star lemma we showed last time. We know q is even. Woo! See, we get a contradiction. So we get both p and q are even. And this is a contradiction. To p, q in the lowest terms. Okay. Well, once we get a contradiction, then we are done. So whatever we assume is false. So square root 2 is not rational. Thus, or therefore, square root of 2 is irrational. Okay, so that finished the proof. Okay, yes, this proof is longer than the previous proof, right? We start with not q, and then think about rational. Rational means is p over q for some integers p and q. And we can assume then they're in the lowest form. Yes. Then we can try to derive some contradiction, okay? And here you can see we also use some lemma, small lemma we prove in the last page. Okay, so that is proof by contradiction. Next topic, proof by contrapositive. Okay, so we call the p implies q and not p implies not q are equivalent. So here are some examples. Give a proof by contrapositive to that for all r x in R, so x is any real numbers. If x squared is irrational, then x is irrational. So this is p. This is q. Okay. The contrapositive statement is not q implies not p. So that means if x is not q, so which means x is rational, then x squared is not irrational, then it's rational. So far, so good, everybody. Okay, and in this case, proving the contrapositive statement is much easier. Think about it, the original one, where x squared is irrational. Irrational, we cannot have a way to describe irrational elements, right? Irrational numbers. But for rational numbers, we know it's like a p over q, okay? So that's why this case, and knowing x squared to get the x is hard because you cannot really take the square root of like both sides, because even though you have like a square root of something, but you're not sure whether that thing is rational or irrational, odd or even. We cannot tell from the square root of that number. Okay, so in this case, it's better to try the contrapositive statement. Okay, so suppose x is rational. Wow, what does that mean? So we know x equals p over q. Bits of notation. Do you mind I still use p and q so they are integers? Okay, but these p and q, I mean propositions. Okay, so for some integer p and q's. Okay. Then now, what is x squared? Well, x squared is then p squared over q squared. Well, you see, they are still integers, right? So p and q are integers, p squared and q squared, they're still integers. So by definition of rational number, we have x squared is rational. So you can see this way is very straightforward. Just by the definition of rational numbers, we get easily. Okay, so that is proof by contrapositive. Let's pause here and we can continue in video part B. See you soon!